Hello everybody, this is Dr. Bricker here with a video for Chapter 2, Motion in One Dimension. So, first couple of chapters, 1 and 2, we just describe motion. In Chapter 4 and 5, then we really talk about what causes this motion. So we're building towards that end. So some goals in this chapter are to describe and also to analyze motion. So by the end of the chapter, we'll have something called kinematics equations, which describe motion in terms of quantities such as displacement, velocity, and acceleration. And we'll have a special case of constant acceleration called free fall. And along the way, again, we'll have the kinematics equations, but we'll also look at this graphically. So as you see in this picture, here's a segue. This is uniform motion, so equal distances in equal time. So this distance is the same as this distance, same as this distance, in equal amounts of time. And that's called uniform motion. Not all motion is uniform motion. If you have a constant velocity, though, you do have uniform motion. Again, not everything is uniform motion, and we'll see that velocities can change. So here's a cheetah that is capable of very large accelerations. So the velocity can change really quickly. The thing with the cheetah is they can't maintain this velocity for very long, but they can go from 0 to 60 really, really fast. That's what allows them to catch their prey. So what you see here is a special case of constant acceleration. This is free fall. So free fall in this case is different than everyday language. In everyday language, free fall if something's moving down. In physics, free fall just means under the influence of gravity. So something could be moving up, something could be moving down. So up or down. If it's just under the influence of gravity, then it's, in the physics way of thinking about it, in free fall. The reason we're concerned about this, if we neglect air resistance, which we can for a lot of different cases, then the acceleration is constant. Okay, so towards the end of the chapter, we'll see that case. Okay, so just like in Chapter 1, if you move to the right, that's where the coordinates are positive. Moving to the left over here, coordinates are negative. Same thing with the coordinate system we use. Up is positive, as you see here, and this is where the coordinates are negative. Now in terms of displacement, remember from Chapter 1, delta x. Delta x is positive if you're going to the right. This doesn't have to do anything to do with where you're located on the number line. This is just moving to the right. Delta x is positive. So remember what delta x is. X final minus x initial. Okay, so that's how we'll represent motion. So what you see here is a position versus time graph. So notice, this is position on the vertical axis. Here's time. Now we're always used to x being on the horizontal axis and y being on the vertical axis. So these are position versus time graphs. So you got to get used to that. Position is actually here on the vertical axis. So we can take different positions at different times and plot them on this graph. So for the initial part, if you notice here, from about 0 to 3 seconds, this is a uniform motion. And it's represented up here too with these vectors. They're all the same. And then we slow down, and that's what you see, this part. And that corresponds to here. And then we speed up. So this is, again, speeding up. So the first part, 0 to 3 seconds, is uniform, sort of the middle speed. Not seconds, but 0 to 3 minutes, sorry. And then from in this region, 4 to 6 minutes, we slow down. And then this region here, we're speeding up again, as you can see from the length of the arrows here, speeding up. Okay, so we'll be able to look at these things graphically, and also then we'll come up with some kinematics equations. So if you do have a position versus time graph, the slope is the rise over the run, just like we had before. So this would be delta x over delta t. And that actually gives us something. It's called the velocity. So the change in position divided by the change in time is the velocity. So we can look at it graphically. The steeper the slope, the faster you're going. So there, the velocity is greater than it is here. It could also be positive and negative, and we'll see cases of that. So what we're seeing here is positive. It could also be negative. Okay, so interpreting position versus time graphs. Whenever you have any kind of graph, the first thing to do is look and see what is being graphed. We'll have position versus time graphs, velocity versus time graphs, acceleration versus time graphs. So the first thing is to note what's actually being graphed. So to determine the velocity from a position versus time graph, you can look at the slope. Let me go back one slide here. So the slope gives you the velocity. So the slope here, I'm looking down here at B. If you get the slope of that line, that is the velocity. It's positive and it has a number associated with it. Same thing for all the different sections. Okay, continuing on then. So from a position versus time graph, you can come up with a velocity versus time graph. So let's see how these correspond. The upper graph here corresponds to the lower graph down here. So the first part from 0 to 3 minutes, there's a certain slope. And it's a line, it's not changing. The slope is what it is for 0 to 3 minutes. Turns out to be 1. So this corresponds to the slope here. And then here, same thing, positive slope, constant. That's this part. And then we have this part. Steeper, but positive. So you can take a position versus time graph and construct a velocity versus time graph. So when I say, make sure that you see what's being graphed, this is the exact same motion being graphed. A position versus time graph looks completely different than a velocity versus time graph. Okay, so that will help us solve some problems. So here's a quick check. Here's a motion diagram of a car moving in a straight line. Which velocity versus time graph matches the motion? Okay, so first thing, okay, down here, these are velocity versus time graphs. So the first 3 arrows here indicate a positive velocity, but it's the same. This, all the same. And then it gets larger. The arrows here are bigger, so it's larger. Also positive, though. Okay, so we have a positive constant velocity, and then in the second part, also a positive constant velocity, just greater. So that corresponds to C. Positive constant velocity, first part, and then the second part is a greater positive velocity. Now, if you had a position versus time graph, you might have selected A. This is what a position versus time graph might look like for this motion, but that's not what we have here. We have a velocity versus time graph. Okay, excellent. So here's a motion diagram of a car moving along a straight line. Okay, so we're going in the negative direction. We're going this way. So negative for the first 3 vectors, and now more negative even than we had before. Same idea as the last one. The first part here, it's the same. The first 3 arrows are the same length. These 3 are the same length. So negative, constant, but more negative for this part. So that corresponds to this graph. Right here we've got negative and constant, and then more negative, still constant though. All right, very good. So here's an example we can take a look at. Draw the car's velocity versus time graph. Okay, so let's see what we actually have here. This is a position versus time graph. So from this position versus time graph, we want to come up with a velocity versus time graph. Okay, so remember, when you have a position versus time graph, you can look at the slope of, if there's any line, look at the slope of the line, and that will tell you the velocity. In some sense, this is the easiest part. There is no slope. The velocity is 0 here from about 2 to 4 seconds. There is no slope. Velocity 0. The sign of that slope is negative. The sign of this slope is positive. So we have a negative velocity, and then no velocity, and then a positive velocity. To get the magnitude of each of these, the magnitude of this part, the magnitude of this part, you have to find the slope, which you could do because you've got the graph there. Next slide. 0 to 2 seconds, our displacement's -4, so the velocity is -2. The second part, from 2 to 4 seconds, we don't have any change in position, so you're not going anywhere, the velocity is 0. And then the second part, this is the slope, 5. So delta x was 10 over 2 seconds, 5 meters per second. Okay, so you see constant negative velocity, 0, and then constant positive velocity. Excellent. So probably different parts of your brain that you haven't used before might start to work because you haven't seen time maybe beyond the x, the so-called x-axis. Horizontal axis is a better way of saying it. Okay, so what's going on? Well, you're going in the negative direction. You stop, you turn around, and then you go in the positive direction at a quicker rate. All right, very nice. So from velocity to position, you could do it in reverse. So let's look at the velocity graph. The velocity is positive and constant. Down here, it's negative and constant. So we know that the slope on a position versus time graph for this graph would have to be positive. The slope on a position versus time graph for this segment has to be negative. So this corresponds to this, and this part corresponds to that. So 1 meter per second for the first 15 seconds, that means the slope has to be 1 of a position versus time graph. And if the velocity is -3, from 15 to 20 seconds, the slope of this line has to be -3. All right, very nice. A graph of a velocity versus time for a hockey puck shot into the goal appears. And we want to figure out what the velocity versus time graph looks like. Okay, so positive velocity, no velocity. So here is where it actually stops. Okay, so constant positive velocity for the first part. That means we have to have a slope on a position versus time graph. So for the first part, we have to have some kind of change in position to give us a velocity. That's the first part. And then the second part, the velocity is not changing. Okay, so wherever we got to, we're just going to stay there. So which one looks like that? It looks like choice D. Okay, good. So you might say, well, why doesn't the position go back to 0? Well, you don't go back to 0. You go to where you're going, and then you stop. And that's what we have here. We are going to wherever we want to go, and then we stop. This is the stopping part. X is not changing with time. All right, very nice. So again, uniform motion is just a special case. As you see here, position versus time graph, if you have a line, a linear function like this, every point, it's a line, so every point on the line has the same slope by definition. Okay, so equal distances in equal times. So we've seen this before. Rise over run, that gives you what the velocity is. Do a little bit of algebra to this equation here. And T final minus T initial is delta T. You can put that in. You come up with this equation. So X final is equal to X initial plus velocity times time. Okay, so just another way of rewriting this equation. All right, good. So here's a quick check one. Here is the position graph of an object. At 1.5 seconds, we want to know what the velocity is. So 1.5 seconds is about here. Whoops. About that location. So what is the velocity here? Well, it turns out anywhere between 1 and 2 seconds has the same velocity, right? Because that's a line. We just have to figure out the slope of that line. So the slope between 1 and 2 seconds would be delta x. So from 0 to 20. So 20 meters in 1 second. So 20 meters per second. So anywhere between 1 and 2 seconds, the velocity is 20 meters per second. All right, very good. Here's an example we can take a look at. A train is moving due east at a constant speed. Okay, good. So equal distances and equal times. A passenger notes it takes 10 minutes to travel 12 kilometers. How long does it take to travel 60 kilometers? So notice 60 is 5 times bigger than 12. So my guess would be 50 minutes, right? If it takes 10 minutes for 12, it's going to have to take 50 minutes to go 60. This, again, is a special case, uniform circular motion. Now, if you're in your car with cruise control on, you can kind of use the same idea. You're going to West Lafayette at whatever the speed limit is. Just say 60. I think it's actually more. And you have 60 miles to go. How long does it take to go 30 miles? Well, that would be half of an hour then. That sort of thing. So if you are traveling at a constant speed, this is useful. You're not always doing that, though. Good. So the ratio of time is, the ratio of distances actually is 5. This is what's given in the problem. 60 over 12 is 5. So 5 times further distance-wise would be 5 times further in time. So if we had 10 minutes before, now we've got 50 minutes. Okay, very good. So here's another example we can take a look at. A soccer player is 15 meters from her goal. She kicks the ball hard. After a half a second, it flies past a defender who stands 5 meters away and continues towards the goal. How much time does it take the goalie? How much time does the goalie have to move into position to block the kick from the moment it leaves the kicker's foot? Okay, so let me kind of draw this out here. Let's just say that this is the goal, and the soccer player is 15 meters away. So here's where the ball initially is, 15 meters away. She kicks the ball hard. After half a second, it travels 5 meters. So after half a second, the ball is here. Whoops. So that takes 0.5 seconds. And this distance was 5 meters. Okay, so the player is here, kicks the ball. It takes a half a second to go 5 meters. How much time does the goalie have? So maybe the goalie is over here. So the ball is going to do this. The goalie is over here. Something like that. How much time does the goalie have to move into position? It's the same idea. If it took 5 meters to go a half a second, how long is it going to take to go 15 meters? So if you think about it like this, half a second, another 5 meters, another half a second, another 5 meters, another half a second. So the total time then would have to be 1.5 seconds. T, I'll put sub T for total, whatever you want to call it, 1.5 seconds. Again, the reason is 5 meters for a half a second, we're going 3 times as far, right? This is 3 times as far as that, so it's going to take 3 times as long. So these are directly proportional to each other. There's nothing square, there's no 1/2s thrown in. Those are directly proportional to each other. Okay, this works because we have uniform circular motion. All right, let's go on to the next one, and then maybe look at one of the homework questions. The displacement is equal to the area under the curve. Yeah, if you think about it, delta x, let me just rewrite this equation a little bit. Delta x, velocity, times time. This little sub x just means it's reminding me that I'm just talking about the x direction. Let me rewrite it because that doesn't look as good as I wanted it to. It's a subscript. Yeah, this doesn't mean times time. So delta x, x velocity times time. You can call it delta t if you want to. I just called it t. So if you were to take the velocity, that's this part, multiply it by the time, that's this part, that gives you the area under a curve. So if you have a velocity versus time graph, the area under the curve is the displacement. So the area under a velocity versus time graph is the displacement. So let's take a look at this problem 218. Okay, so let's see if we can set this one up. A somewhat idealized graph of the speed of blood in the ascending aorta during one beat of the heart is shown in this picture here. And we want to know approximately how far in centimeters does the blood travel during one heartbeat. So what we have is a velocity versus time graph. We want to figure out the displacement associated with that. So just like we said in the last problem, if you have a velocity versus time graph, the displacement is the area under the curve. So this is not a nice square or rectangle like we had before, but it still works for this shape. So this is a triangle. We need to get the area of this. So the area of a triangle, if you remember, is 1/2 the base. This is the base, 0.2 seconds, right? From 0.4 down to 0.2. So 1/2 this times the height. And it looks to be the height's about 7.5 meters per second. Now be careful, we want the answer in centimeters. So if you get the area under this curve, it'll be in meters. You'll have to convert it into centimeters. Okay, so area under the curve, 1/2 base times the height, and then convert it to centimeters. And then the second part here, assume similar data for the motion of blood in the carotid artery, which connects the aorta to the brain. Estimate how many beats of the heart it will take to get blood from your aorta to your brain. All right, so you'll have to use how far you got for one heartbeat and figure out how many beats it takes you to get all the way up to 30 centimeters. You might be kind of surprised about the answer. So if you take your pulse and think about blood going from your aorta to your brain, you'll see how many actual heartbeats it takes. Okay, pretty cool. All right, let's see what else we have in store. Okay, so we've got this idea of instantaneous velocity. Instantaneous velocity is what you actually see on your speedometer. It's how fast you're going at that instant. Now, sometimes instantaneous velocity and what we've seen before with uniform circular motion, those would be the same thing. If the velocity is not changing, instantaneous is whatever it is. But if it is changing, instantaneous means how much is it right at that instant. So here's a graph of position versus time where the motion is not uniform. So let's first see what's being graphed. Position, whoops, go back. Position versus time. Let me rehook this up. Position versus time. So here we've got position, here we've got time. But this is not a line. This doesn't change in a linear fashion. So how can we figure out what the instantaneous velocity is? Well, we can pick a point and find the slope of the tangent line right at that point. So you can get pretty close if you pick a point. All right, let's see kind of what the slope is. Let's make the time increment smaller and smaller and smaller. So in the word of mathematicians, let's take the limit as delta t goes to 0. And what that actually gives you is the slope of the tangent line. So I have to pick out a point and get the slope of the tangent line there. So here's a blown up picture of what you saw on the previous slide. So if the velocity changes, the position graph is a curved line, and that's what we see here. This is not a nice straight linear function, but that's okay. We could get the slope of the tangent line at a point. So let's look around, as it says here, about 0.75 seconds and see what we could figure out. So around 0.75 seconds, delta x is 1.6 and delta t is 0.2. So right around that point, when you make the time increment smaller and smaller and smaller, then you approach its actual instantaneous velocity. So the takeaway from this is, if you have a graph, the slope of the tangent line gives you the velocity. So let me just draw one something like this. Whoops. So let me pick a point here. Whoops. Okay. And I want to know the instantaneous velocity there. So at this point, there's a tangent line. This is x versus t. So here's a tangent line. So the slope of that tangent line is the instantaneous velocity. Okay? As it says here, the slope of the tangent line. Now, we probably won't be drawing x versus t graphs and carefully plotting out the what the instantaneous velocity is there, but that's something that we should know. It's the if you do have an x versus t graph, the slope of the tangent line gives you the velocity. So we'll use that information to solve some other problems. So here's a velocity versus time graph. Same thing as we had before. The area under the curve is the displacement. This is not a nice triangle or rectangle, but it still works. The area under this curve is the velocity. So calculus was actually invented to calculate this sort of thing, the area under the curve. So here's an example we can take a look at. The displacement during a rapid start. So we go from not moving, velocity of 0, up to about 12 meters per second. We want to know what is the displacement during this time. In other words, how far does the car travel during the first 3 seconds? So if we can get the area under this curve, we can solve for the displacement. So kind of like the heartbeat one, the area is 1/2 the base. This is the base. So 1/2 the base times the height. That'll give us the area under the curve. So in this, you can't just take like 12 times 3. 12 meters per second times 3 seconds. Okay, that gives you something, but that doesn't give you the area under the curve. Now, if you had uniform velocity, you could do velocity times time gives you the displacement, but that's not what we have here. The velocity keeps changing. It goes from 0 to 4 to 8 to 12 to 16. So it's not the same the whole time. You could take the average velocity, which would be half of 12 in this case, take half of the final velocity. So half of the final velocity would be 6, and that would be the average. Multiply it by 3, and then you would get the displacement that way. That's just another way of doing it. Just think area under the curve is the displacement. Okay, and that's what we have here. 1/2 the base times the height. So 18 meters then. All right, very good. Here's a kind of a fun one. A car moves along a straight stretch of road. The following graph shows the position as a function of time. And we want to know when is the, at what points do the following conditions apply? Where is the position 0? Okay, so in other words, when is x equal to 0? Well, x is equal to 0 only right here. That's just where the coordinate is equal to 0. Where is the speed 0? So if you look at what we have here, position versus time, here's the slope of the tangent line. Here's the slope of the tangent line. Those are the positions where the velocity is 0. You're not moving anymore. Okay, where is the velocity negative? So where, in other words, is the tangent line negative? And then the last one, where is it positive? So if you take a look at this, the velocity is negative at C and D. So here's the tangent line at C. Slope is negative. Same thing with D. And then here at A, slope of the tangent line is positive. So let's take a look at 2.22 from the homework. Okay, so we set the origin of a coordinate system so that the position of a train, when x is equal to 0, it's located at 0. Okay, that makes sense. This picture here shows the train's velocity graph. And from that, we want to figure out the position graph. We've got several choices here. Again, like if you want to review the section of the book, hit review and the book will pop up for you. So let's see what's going on here. So from 0 to 4 seconds, the velocity is positive. That means we're going in the positive direction. And then at 4 seconds, the velocity is constant. Now that doesn't mean we stop. That means we're at 2. meters per second, and we're going to stay at 2 meters per second. So think of what a position versus time graph would have to look like from 4 to 10 seconds. Okay? And then here the velocity keeps getting bigger and bigger and bigger, so the slope of the tangent line has to keep getting bigger and bigger and bigger. So let's just go through these. In this one, see, they tell us we start at 0, so this is not going to make any sense. This is starting at 2. Plus, for the first part, here's where the velocity is 0. That doesn't make any sense. Okay, this one is starting at 0. That one's starting at 0. That one's starting at 0. Okay, so those are possibilities. Okay, so good. So slope of the tangent line here would be positive all the way to 2 seconds. Then the velocity is 0. And then the slope of the tangent line is negative. And then it stays negative. So this one's not going to work. Slope of the tangent line here is saying that the velocity should be positive, and it's not. The 0 velocity part works okay, right? The slope of the tangent line is 0 at 2 seconds. The velocity is 0 at 2 seconds there. All right. So we're down to these two choices. Let's look at this one first. So on this one, from 0 to 2 seconds, the velocity is 0, right? Position versus time. The position's not changing, not changing, not changing, all the way till 4 seconds. So that doesn't work. As you can see here, the position has to be changing because we have some kind of velocity. So it's going to be this choice. Slope of the tangent line negative, tangent line getting less and less. Slope of the tangent line 0 at 2 seconds, meaning the velocity is 0 at 2 seconds. Slope of the tangent line getting more and more positive. Velocity getting more and more positive until we hit this linear region. So then here's where the velocity stays at 2. So it's got to be this choice here. All right, so that's pretty cool. Take a velocity graph, reconstruct a position graph from that. All right, let's get back to the notes. Okay, so we've got displacement, velocity. Now we have acceleration to take a look at. So acceleration is the change in velocity divided by the change in time. So it could also be positive or negative. It's a vector quantity. So in our SI unit of velocity, just as a little reference, 60 miles per hour is about 27 meters per second. So the Corvette speeds up 27 meters per second in 3.6 seconds. It has a really big acceleration. So from 0 to 60, it only takes 3.6 seconds. Whereas a Chevy Sonic will take 9 seconds. They can both get up to 60 miles per hour, but the Corvette does it a lot faster than the Chevy Sonic. So we can say it has a greater acceleration. Here's an example. Lions, like most predators, are capable of very rapid starts. So from rest, a lion can sustain an acceleration of 9.5 meters per second squared. By the way, that's the unit of acceleration. If you think about it, let me go back. We have meters per second, as you see here. This is completely a nice way of saying it. After a second, you've changed the velocity by a certain meters per second. It's also completely correct to say meters per second squared. You just kind of lose the feeling for what that means. Like, what is a second squared? Well, really, that comes from meters per second per second. Usually you write it meters per second squared, but if you really think about what it means meters per second, per second. How fast is the velocity changing? Okay, good. So let's see what we have here. A lion can sustain an acceleration of 9.5 meters per second every second. So every second the velocity changes by 9.5 meters per second, but only up to 1 second. So how much time does it take a lion to go from rest to 10 miles per hour? So as soon as you see 10 miles per hour, you have to do something with it. We've got to convert it to meters per second, which is being done right here, actually. Here's the conversion factor. Okay. So good. So 4.5 meters per second. That's what we want to know. How fast does it take the lion to do that? So we know the acceleration of the line is given. We've got, but it only can do that for 1 second. Luckily, we're not actually going to have to use the whole second, because in 1 second the line can get up to 9.5. We only want the line to get up to 4.5. Okay? So we can take the equation that we had before, just do a little bit of algebra. By that I mean this. Acceleration was delta v over delta t. So if you solve for delta t, multiply both sides by delta t, divide both sides by a. That's where this equation comes from, that you see up here. So we get 0.47 seconds then. So half a second to go 10 miles per hour. That's pretty impressive. Now, if we were to graph velocity versus time for both the Corvette and the Sonic, we'd see something like this. Velocity versus time. Remember, first thing to do is look and see what's being graphed. So the slope of a velocity versus time graph gives you the acceleration. So the Corvette slope is much greater than the Chevy Sonic's slope. Okay. The table over here just shows some data at different points used to create this graph. We don't know this yet, but greater accelerations take greater forces. So if you have a velocity versus time graph, you can build an acceleration graph from that. So let's look at this part first. The velocity is not changing. Delta V is 0. So there is no acceleration for this part. Here the velocity is increasing at a uniform rate, so we've got constant acceleration. That corresponds to this part. Here the velocity is getting less and less, so the acceleration is negative. Now the magnitude here is not as great as the magnitude here. This is steeper. This is less steep. Okay? Good, so we've got position versus time, velocity versus time, and now acceleration versus time. We're not going to be doing the change in acceleration graph in this class. We stop at just uniform acceleration, or no acceleration. Things changing at a velocity changing at a uniform rate. Okay? So when can the acceleration be positive? Here's a couple of examples. If you just think about it graphically, this slope is positive. This slope is positive. The one on the left here, the velocity is positive and getting more and more positive. The one next to that, the velocity is negative and getting less and less negative. So that's where the acceleration would also be positive. Our brains typically think like the graph on the left. The acceleration could also be negative. So the slope of velocity versus time graph has to be negative. So the one on the left here, the velocity is positive, but getting less and less positive. You're slowing down, so the acceleration is negative. Here, same thing, the slope is negative. The velocity is negative and getting more and more negative, so the acceleration is negative. Okay, and you can see that also from these motion ways of looking at it. Okay, excellent. So here's a little test we could take a look at. A cart slows down while moving away from the origin. So the cart is on the x-axis, moving away from the origin, and it's slowing down. Okay, so the velocity is positive, but becoming less and less positive. And we want to know what do the graphs look like. So why is it d? So the velocity has to be positive and becoming less and less positive. This is the only graph that actually corresponds to that. If you notice, the velocity is positive in the beginning and then getting less and less positive. So I think for this one, pick out the velocity graph and then see if the position graph makes any sense. This is the only velocity graph that actually works. Let's see if the position versus time graph goes along with that. Slope of the tangent lines on this graph are positive, but getting less and less positive. Good. So that's the only one that actually makes sense. A here has the velocity getting faster and faster and faster. Here the velocity is negative and becoming more negative. Here it's negative but becoming less negative. It's not that. The velocity is positive and becoming less and less positive. Here's another one. A cart speeds up at a constant rate away from the origin. Okay, so speeding up, it's moving away from the origin. The velocity is positive and becoming more and more positive. Let's see if we could weed any of these out. Can't be this one. That one's telling us that the velocity is constant. And they tell us in the problem it's getting faster and faster. Okay, so it could, just based on velocity, be B, C, or D. The velocity is correct for all of those. Now, the only one where the acceleration makes sense, though, here is choice B. So this is a nice uniform increase in velocity. That means the acceleration is constant. And that's what we have here. Remember, acceleration is the slope here. And it's a line, so this is constant. Okay, let's look at 2.27. Okay, so for this problem, we've got a Thompson's gazelle can reach 13 meters per second in 3 seconds. A lion can reach 9.5 in 1 second. And a trout, of all things, can reach 2.8 in 0.12 seconds. Which has the greatest acceleration? So for this one, actually go through each of them and figure out the acceleration. The acceleration is delta V divided by delta T. So let me just do the gazelle one. The change in velocity is 13. The time is 3 seconds, so 13 over 3. And then do the same thing for the lion and the trout, and then figure out which one has the greatest acceleration. Okay, back to the notes. Okay, next section is motion with constant acceleration. So here we're going to develop some kinematics equations. So here's a graph of velocity versus time. This is some data for this craft here, lifting off. So the acceleration is delta V over delta T. Now the little y here just means y direction. Same thing here, velocity and y. Pretty much everything we've done so far has been the x direction. But here's one where we have the y direction. We can figure out the acceleration. This is a line here, so we've got uniform acceleration. This is a line for the velocity versus time graph. So delta V over delta T, 18 meters per second per second. So every second this thing increases by about 18 or so meters per second. So if I want to, I could take that equation and rewrite it and get our first kinematics equation. So acceleration, change in velocity divided by the change in time. I could just do a little bit of algebra to that and solve for the final velocity, and I get my first kinematics equation. Final velocity is equal to initial velocity plus AT. So final is equal to initial plus A times T. Now they have delta T there, but almost all the time we start with the clock at 0, so delta T and the final time are the same thing. Now final doesn't mean that you've stopped, it just means later. Initial means what you started with. So this is what you started with, this is what you ended up with. And you can call these things whatever you want to. I've seen books do it like this. V2 is equal to V1 plus A times T. The little x here in the formula just says, oh, we're talking about the x direction. You're doing the problem so you know which direction you're talking about. If you want to include it, that's completely fine. I usually don't, just to save a little bit of time. Now when I start to do two-dimensional motion, I might do x and y because I don't want to mix them up. Good, so we've got our first kinematics equation. By the way, all the kinematics equations will be for constant or zero acceleration. Okay, so here's a graph of velocity versus time. You can see down here in B. We can use this to come up with another kinematics equation. And we want to get the area under the curve. So the area under the curve would be the lighter area here plus the darker area here. That's where this equation actually comes from. 1/2 the base times the height. So I'll leave it to you to look up the derivation of that in the book. But essentially it's this. For the lighter color, delta T times the initial velocity. That will give you that area. Then you've got to take that area and add it to the area of the triangle. Same time, delta t. Here is the height, though, a times t. So if you take delta t times the initial velocity plus 1/2 delta t times a times delta t, that gives you the displacement. You could rearrange the equation a little bit and come up with our second kinematics equation. I usually write this kinematics equation like this: delta x initial velocity times time plus 1/2 a t squared. It's the same thing. They just have x final and x initial separated. I've combined them together. Good. So that'll be our second kinematics equation we have. And then finally, if you take a look at this one, this equation has final velocity, initial velocity, acceleration, and time. Perfectly good. This equation that we've just came up with doesn't have final velocity, but it does have displacement. The first one doesn't have displacement. The second one doesn't have final velocity. So depending on what you're looking for, maybe you use the first one, maybe you use the second one. They both have acceleration and they both have time. What if you don't know anything about the time, but you want to figure out the displacement or some other quantity? You can take the first equation and second equation and solve for t in one of them, plug it into the other one, eliminate time, and come up with a third kinematics equation. So velocity final squared is equal to a velocity initial squared plus 2a times delta x. This is the third kinematics equation. This one does not have time in it, but it does have final velocity, initial velocity, and delta x. And again, they all have acceleration in them. It's good. So we've got these three tools in our new physics tool belt that we can use to solve a lot of different problems. Now, this is kind of a summary of what I've just said. You know, which equation do you use? Well, you have to know what you're given and what you're looking for. Sometimes you have to use two of them in the same problem. Okay, here's a problem we can take a look at. As you drive in your car at 15 meters per second, which is about 35 miles per hour, you see a child's ball roll into the street ahead of you. You hit the brakes and stop as quickly as you can. In this case, you come to a rest in 1.5 seconds. How far does your car travel as you come to stop? Lots of different ways of looking at it. If you think about it, here's the motion diagram part right there. Here's what the velocity versus time graph looks like. You could actually solve this problem just by getting the area under the curve, or we could use our kinematics equations. Okay, so first of all, knowing the velocity and the time, the change in velocity really and the change in time, we can figure out the acceleration. That's what's being done in the first step here. And it turns out to be negative because we're slowing down. And then once you have the acceleration, we could use this kinematics equation to figure out what the displacement is. That's what's being done there. Plus 1/2 a/t squared. Okay, and then from that, you get the displacement. You could have just got the area under the curve if you wanted to, or we could get, having the acceleration, use kinematics to solve it. It's good to know multiple ways of doing problems. So be careful with the units here. If you notice, this is 15 meters per second times 1.5 seconds. That turns out to give us meters. Now, if you forgot the negative sign here, you would get the incorrect answer. And then we've got meters per second squared times second squared. That leaves us with meters. So meters plus meters. All the units work out correctly. Okay, very good. So 11 meters is a little bit over 35 feet. Reasonable if you're traveling around 35 miles per hour. Okay? Very good. So this is similar to 2.37. The problem that we just did assumes like you immediately slam on the brakes. 2.37, you actually travel some distance before you realize you have to slam on the brakes. So we'll talk about that next week in class. Just keep that in mind if you're working on that ahead on that one. This problem we'll come back to when we talk about free fall. Spud Webb, basketball player from, I believe, the 90s. Okay, Here's another one we can take a look at. A drag racer starting from rest travels 6 meters in 1 second. Suppose that the car continues its acceleration for an additional 4 seconds. So this is not uniform motion. The velocity is changing. So going from rest, travels 6 meters in 1 second. You can't say that they're going 6 meters per second at the end of that time. That would be the average velocity over the whole amount of time, but we don't know how fast the racer is going exactly at 1 second. So suppose the car continues its acceleration for an additional 4 seconds. How far from the starting line will the car be? Good, so you can do it in several ways. Draw a little picture if you want to, however you want to approach that. Let me write some information down and show you how I would solve this. Okay, so here's what we have. Starting from rest, you travel 6 meters in 1 second. We want to know how far you are after 4 seconds. So you have in the notes the way that the author solved it. I'm just going to do it a different way so you have another perspective on this. Now, if I wanted to figure out how far I traveled, I could actually use this formula. If I knew what my acceleration was, I can figure out how far I've traveled. So these are just our general 3 equations here. So initial velocity, I call this delta x1. So 6 meters in 1 second. We want to know what delta, I'm just calling it delta x2. You can call them whatever you want to. What would that be after 4 seconds? So the velocity keeps changing. It's not, you can't just multiply, this is 4 times longer in time. You can't just multiply that by 4 because it's not a linear relationship. Remember, it's 1/2 at squared. So this displacement depends on the time squared. I could do it like this, actually. Because we're both starting from rest, I could say delta x1 is equal to 1/2 a t1 squared. Remember, the initial velocity is 0, so that term becomes 0. And I could do this. Delta x2 is initial velocity times time, which again, that's 0, plus 1/2 a t2 squared. This is a way of avoiding figuring out how much the acceleration is. It's kind of actually similar to what the author does. I'm just showing you the why. Now, if I take this side and divide it by this side, something nice happens. Delta x1 over delta x2. The 1/2s and the a's cancel out. This would be t1 squared over t2 squared. And then I can solve for delta x2. That's what I'm trying to find out. So I'm multiplying both sides by delta x, however you want to do it. Flip it over and then multiply both sides by delta x1. I'll leave you to figure out the algebra part of it. I'm just going to give you the answer here. Delta x1 t2 squared over t1 squared. So from this step to this step, I'm out of room, so I can't give you all the steps, but you can take the reciprocal and then multiply both sides by delta x1, and then you get this. And this is similar to what you saw on the way it was worked out. I'm just showing you where it actually comes from. So this would be 6 meters times this t2 squared, 4 seconds squared, divided by 1 second squared. Good, and that's why it's so much bigger than it was before. Okay, so hopefully I've got all the numbers right there. I think it looks good. Okay. Actually, I goofed something up. This is 4 more seconds. This is a total of 5 seconds. This is 5 seconds. So that's how you get 150 meters then. The problem was worded 4 additional seconds, not at 4 seconds, 4 additional seconds. So that would be after 5 total seconds. Okay, very good. Okay, so this section is on solving some problems. So a good place maybe that you won't start initially, but you can fall back on, is thinking about motion diagrams. You know, kind of visualize what's going on. Maybe even draw a picture. That can help out. Maybe a graph helps. You definitely want to write down your list of values. So I always write down what I know, what I'm looking for, and then I draw a picture. Now on a test, if you did that, you'd probably get 3 or 4 out of 10. So part of this is learning how to solve problems, and to me, you've got to be organized to do that. So write down what you know, what you're looking for, and maybe a picture will help. So kinematics of a rocket launch. Saturn rocket is launched straight up with a constant acceleration. After 150 seconds, how fast is the rocket moving and how far has it traveled? Okay, so launched straight up, we're assuming it's launched having no initial velocity and then it's launched. So sometimes you have to bring information into the problem on your own. So in this problem, the initial velocity is 0. It doesn't say that, but that's what's true. That's what has to have been true. The acceleration is 18 meters per second per second. So after 150 seconds, how fast is the rocket moving and how far has it traveled? So we got a nice picture. We've got a nice motion diagram going on. Over here on the left is what we know. And then here's what we're looking for at the bottom here. And we've got the 3 kinematics equations to work with. So the first one that we had was actually this. The final velocity, final velocity, pen wasn't working, now it's back. Final velocity is equal to the initial velocity plus AT. So this means earlier, final means later. And again, we're assuming the initial velocity in the y is 0. So that's the equation that's being used here. So this term is 0. So it's a times t. That'll give us the velocity after 150 seconds. But we're also looking for really how far have we gone in the y direction. The equations I wrote before were in terms of the x direction, but they also work for the y direction. So if I want to write this one in terms of the y direction, delta y, initial velocity in the y times time plus 1/2 acceleration in the y times t squared. That's the second kinematics equation that we came up with. Same thing, this term is actually 0 because we're starting from rest. So 1/2 AT squared it turns out to be. So 1/2 18 meters per second squared times 150 seconds and then square it. If you put all that in, you get 2 times 10 to the 5th meters, which is the same thing as 200 kilometers. Okay, excellent. So using some kinematics equations. Definitely have those on your formula sheet for the first test. You could already start building that. I mean, it's a tool that you could use for the homework. And then when it comes time for the test, you don't have to completely do one from scratch. Okay, so I included this one in the slides. This one's actually all worked out for you. I'll just say a couple of words about it. Here's the motion diagram. Here's the little picture of what's going on. Here's what you know. Here's what you're looking for. And then you have all the kinematics equations to use. And, depending on what you're looking for, you sift through the kinematics equations and then pick out whatever part of it that you actually need. And that's what's actually done here for you. So I won't go through all the details, but that's the motivation for it. Again, I usually write this one in this form, delta x, initial velocity times time, 1/2 AT squared. Same thing that you have written there. I just usually do delta x instead of x final and x initial. Same exact thing. Okay, good. So take a look through there. So let's look at a couple more examples from the first homework, and then we will talk about free fall. Okay, so this is 2.32. Light rail passenger trains provide transportation within and between cities, speed up and slow down with a nearly constant and quite modest acceleration. A train travels through a congested area at 6 meters per second. Once free, it speeds up to 14 meters per second in 8 seconds. At the edge of town, the driver again accelerates with the same acceleration for another 16 seconds to reach a higher cruising speed. And then what is this final cruising speed? So we definitely need a little picture for this one. Let's take a look at it. Okay, so we're at 6 meters per second. We go up to 14 meters per second. This happens in 8 seconds. And then we've got another 16 seconds at the same rate that we accelerated here. What is this final speed? Here's what we have to use. V final, V initial, plus AT. Change in x, initial velocity times time, plus 1/2 at squared. These are our new tools that we have. Velocity final squared is equal to a velocity initial squared plus 2a delta x. You can call these things whatever you want. I'm going to say this is v1, this one's v2. I'll just keep that as v final. Okay, so we don't know anything about displacements in this question. They don't give us delta x's for anything. We do know times. Maybe I'll call that one t1, this one t2. Okay, very good. So if I can figure out the acceleration here, I could use that acceleration over here to figure out what that final speed is. So this is what I'm saying. From this first part, I could say v2 is equal to v1 plus a times t1. And that's perfectly good. I know v2 and I know v1, earlier and later. I know the time that happened in, so I can figure out the acceleration. The reason I want to do that is then over here I could say v final later is equal to earlier plus a times t2. And this a, they tell us, is the same as this a. So if I can figure out the acceleration from this part, I could use it over here to figure out that velocity. Lots of different ways of doing this problem, by the way. Maybe you've come up with a different way. Okay? Yeah, you can almost just reason this one out, actually. No, but we'll talk about that in just a minute. Okay, so a little bit of algebra here. v2 minus v1 over t1 gives you a. So I've subtracted v1 from both sides, divided both sides by t1. So v2 minus v1 would give me 8 meters per second. This happened in 8 seconds. So the acceleration is 1 meter per second squared. And then I can come over here and figure out this final speed, because now I know the acceleration. 14 meters per second plus 1 meter per second squared for 16 seconds. A little bit out of room there. That's a 16, believe it or not. So this turns out to be 30 meters per second. Okay, so our final speed here would be 30 meters per second. So this is a nice linear relationship between speed and time. So if you think about it, in 8 seconds our speed increased by 8. So in 16 seconds the speed's going to have to increase by 16. So if we started at 14, this is going to have to be 30. We can do that with this problem because the equation that we used, nothing is squared. The displacement, if you remember earlier, depended on the time squared. This one we don't have displacement. Final speed and time are proportional to each other. Okay, and we got one more to look at. Okay, so this one I want you to take a look at before we meet next time, and we could talk about it then. It's similar to one that we did before. This is 2.37. The only difference, and I just wanted to say this about this one, there's a reaction time before anything even happens. So a driver has a reaction time of 0.5 seconds. So for 0.5 seconds, she doesn't do anything. A driver has a reaction time of 0.5. What is the maximum deceleration of her car? And the maximum deceleration is 6. So the acceleration, in other words, is -6. She's driving at 20 meters per second when suddenly she sees an obstacle in the road 50 meters in front of her. What is the distance she passes after noticing the obstacle? Okay, sorry, the UPS guy who just knocked on the door. So anyway, take a look at this one, and we'll talk about it in class. But the only difference really for this one is you're going to travel a certain distance before you even hit the brakes. So you have to take that into consideration for the overall distance. Okay, let's look at the next bit of the notes. So now with free fall, we can also use all of our kinematics equations. It's just with free fall, we already know how much the acceleration is going to be. The acceleration is going to be negative 9.8 meters per second squared in the y direction. Let's see how we can use this. Again, I said it at the beginning of the notes today. Free fall means under the influence of gravity. So in the way physicists look at it, and the way we're going to look at it, things going up, things are going down. Just under the influence of gravity, it's free fall. So it doesn't literally have to be going downward. Okay, and here's a famous picture of astronaut David Scott from Apollo 15 performing a classic experiment on the moon, simultaneously dropping a hammer and a feather, and they both hit at the same time. So try this. Drop a dollar bill and a quarter. Now you can imagine that the quarter is going to hit the ground first. Now do this experiment. Take the dollar bill, wad it up into a small shape, then drop them both, and then they both will hit the ground at the same time. We'll see that in class next week as well. So here's a graph of velocity versus time for free fall. So the velocity is changing at a constant rate, negative 9.8 meters per second squared. Here's the motion diagram on the way up and on the way down. So same thing, acceleration negative 9.8. So in a way, this makes our life a little bit easier. For all the kinematics equations we have, we know what the acceleration is. Let me just show you one more thing about this. Okay, so let me draw a velocity versus time graph. Let's move it over here. So here's velocity, here's time. Now what I'm going to do is throw something in the air and have it come back down. So it's going to start after it leaves my hand. That's what I'm graphing here. After it leaves my hand, it's heading up and then it's coming back down. So on the way up, after it's left my hand, whoops, the velocity is positive. This is on the way up. Velocity is positive, but becoming less and less positive. This is the highest point. That's the maximum height, I guess I'll call it. And then on the way down, the velocity is negative. So this is free fall, even though, again, it's going up, stopping for an instant, coming back down. And here, the acceleration is negative 9.8 meters per second squared. Now we can use all of our kinematics equations that we had before. So by that I mean this. Final velocity, and I'll just put a y to emphasize that, is equal to initial velocity. I'll put a little y to emphasize that, plus 1/2 at, and that's in the y direction. Second one, change in y, initial velocity in y, times time, plus 1/2 a in the y direction, t squared. And then finally, final velocity in the y squared, initial velocity in the y squared, plus 2a delta y. And what we know now for these problems, the acceleration in the y is negative 9.8 meters per second squared. So we have to bring this to the problem. Any of these free fall problems, when we're just under the influence of gravity, we know the acceleration. So this one, this picture here doesn't really go along with what's going on here. It's just for illustrative purposes. This one, it's going up and then coming straight back down. And we just saw that from what I just worked out. This one here, velocity is positive. It gets less and less positive on the way up. At the highest point, it's 0. And then on the way down, it's negative. Okay, so in class next week, we'll do look at these last 3 problems from the homework assignment. Okay, I included them here, this worked out problem too, so you can take a look at this one, and then in class we will take a look at those questions, and then also finish up any other homework 1 questions. Okay, if you have any questions, send me an email, and I'll talk to you soon. Oh, by the way, I included, when you look at the PowerPoint, the summaries just for your benefit. Okay, excellent. Have a great day. Email me.